So in this video, we're going to talk about the fundamental identities in trig. And the first thing I want to remind you of is the test for symmetry, because that will help me talk about the first set of identities. So we talked about in some other videos, the test for symmetry was taking f of negative x. So plug negative x into your equation. And if you go through and you calculate what this is, and then you get that f of negative x just gets you back to the original function f of x, your function will be even. And it's odd if you plug in that negative x and then you get the negative of your function. So just a reminder of these definitions. And so I'm bringing that up because I've talked about in previous videos that we know sine is an odd function. And so what that means then is if f of x equals sine of x, then if I plug that negative x in, if sine is odd, I know that sine of negative x will equal negative sine of x. This is what it means to be an odd function, right? So I just want you to remember this. Sine of negative x equals negative sine of x. And then we also know that cosine is even, so just using kind of similar reasoning, if f of x is equal to cosine of x, then f of negative x equals cosine of negative x, which will equal just itself, right? So that's what it means to be an even function. So going back to these, right? So if I plug in negative x and I get the function back, that's even. If I plug in negative x, I get negative f of x. So, okay, so this is what it means for cosine to be even. And the big thing I just want you to remember here is cosine of negative x equals cosine of x. All right, so I'm reminding you of those. And the thing is, these little statements here, sine of negative x equals negative sine of x and cosine of negative x equals cosine of x, these are what are known as identities. So these are actually like little facts that we use all the time. Okay, so using these two identities, we can determine one more. So if I take tangent of negative x, so think about what that means. That is the same as taking sine of negative x over cosine of negative x. And I know what each of these equals now, right? I've got those identities. So this will come out to negative sine of x, because that's what sine of negative x is, over positive cosine of x, because that's what cosine of negative x is. So that's what we're just talking about, right? So if I rewrite it like this, this is really the equivalent of negative, or this is equivalent to negative tangent of x. So what we get here then is that tangent of negative x is equal to negative tangent of x. So this is another identity. So these three identities are what are called the even-odd identities. There's actually a list of 6 of them, because once you know the first 3, then you can work through the reciprocals as well. So if cosine of negative theta equals positive cosine of theta, then so will secant of negative theta, right? Because they're reciprocals of one another, so hopefully that makes sense. So these are what are known as the even-odd identities, and these are handy to know because they can just kind of like pop up in places where you're not sure that you need them. And this happens a lot in calculus. So the reason that we talk about this is actually something that you need more in calculus. You need to be able to rewrite things to make it easier to deal with, and that's really where we're going with this. Now, we have discussed a few other identities in previous videos, and now I'm going to remind you of what the other identities are, because we're going to use them. So these identities make what are known as the fundamental identities. So, okay, let's review these. So we have the reciprocal identities, so like cotangent of theta is equal to 1 over tangent of theta, secant of theta is equal to 1 over cosine of theta, and cosecant of theta is equal to 1 over sine of theta. So we've seen these before. And we have the quotient identities, so tangent of theta is equal to sine of theta over cosine of theta, and cotangent of theta is equal to cosine of theta over sine of theta. And then the Pythagorean identities, so sine squared theta plus cosine squared theta equals 1, tangent squared theta plus 1 equals secant squared theta, and then 1 plus cotangent squared theta equals cosecant squared theta. So those are the Pythagorean identities, and then again, these are the even-odd identities. So these lists make our fundamental identities. And exercises about the fundamental identities require you to clearly show how to use them. The point is to kind of get used to using these, because really these are like a list of tricks to help make trig problems easier. That's really the best way I can describe this. So what we're going to do now is we're going to look at a bunch of different examples and show you kind of how to leverage some of these. Okay, so in this first example, we've got if cosine of theta equals 3/4 and theta is in quadrant 1, find sine of theta. So the idea behind this is that you think through like these lists of identities. And what you're really looking for is what identity relates just cosine and sine together. That's kind of the trick with these. And so if you go through that list, you've got the Pythagorean identity, right? So the Pythagorean identity involves sine and cosine only. It doesn't involve anything else. We wouldn't want to use like tangent of theta because tangent of theta involves tangent and sine and cosine. You want an identity that ideally would only relate the two things that you're interested in, if possible, if that's kind of what you're trying to do. So this is kind of ideal. So what I'm going to do is I'm going to remind myself. So sine squared theta plus cosine squared theta, this equals 1, okay? And then I can plug this little piece of information in. So I've got sine squared theta plus 3/4 squared equals 1, because that is the value now of cosine theta, right? And I just square that value. And so you can see now that we could actually go through and basically do the algebra to figure out what sine of theta is equal to. So I'm going to have sine squared theta plus 9/16 equals 1. So sine squared theta equals 1 minus 9/16. And so then I have sine squared theta is going to equal 7/16. And then if I take the square root of both sides, so remember you have to use the square root property here. So I can take the square root to get that sine of theta will equal plus or minus the square root of 7/16. But wait, now how do I know if I want the plus or minus sign? Well, that's when you refer to the quadrant. So you have to think about, in quadrant 1, is sine going to be positive or negative? It's going to be positive, right? All students take calculus. In quadrant 1, all the trig functions are positive. So actually I can erase this plus or minus and give a definitive answer of this is just positive. And I don't even have to write the plus sign, I just wanted to make it clear. But so this would be how you would find the value of sine. And you can do that then by using the identities. So I think we've done some exercises similar to that. Okay, so now I want to turn towards this next one. So if tangent of theta equals -1/4 and theta is in quadrant form, find the values of all the other trig functions. Okay, so let's make a little space. And we'll start by just noting this, tangent of theta equals -1/4. Now from this, I can get for sure cotangent of theta, right? Because that comes from one of the reciprocal identities. Cotangent of theta is just equal to 1/tangent of theta. So this is 1/tangent of theta, so that's 1/-1/4. So that's just going to equal -4, right? So that's it for that one. And that's in quadrant 4. We know tangent is negative in quadrant 4. Okay, so now we have to think of what else can I find. Now you might be thinking to yourself, I want to talk through something that is, let's see, I'll write this wrong. I want to talk about a wrong assumption before I go much farther. And I want you to tell me, or I want you to think about why this doesn't work. So if I know that tangent of theta is equal to sine of theta over cosine of theta, so this equals -1/4, why can't I say this is sine of theta and this is cosine of theta? Well, you don't know if there was some sort of simplification that happened to simplify this. Maybe sine was something really complicated on top and cosine was something really complicated on bottom, and then when you did the division, it worked out to -1/4. You can't make this assumption. So this does not work. So you have to, it's going to take us a little bit of work to figure out what sine and cosine actually are. So I wanted to address that. So let's clear some space. And now let's just think through our identities. So if I go back to my Pythagorean identities, so I know that this identity here will relate tangent and secant, and I can get some other identities out of this, right? So I'm going to use that identity next. And I want you to note how I actually write out, so tangent squared theta plus 1 equals secant squared theta. So when you're using identities, I think one of the hardest things about it is trying to show your work. I think this is a really great way to show your reasoning, writing out the identity. And now I can just plug in this part of the identity. So I've got negative 1/4 squared plus 1 equals secant squared theta. And so this becomes 1/16 plus 1 equals secant squared theta. So what we get then is secant squared theta will equal 17/16. And then I can take the square root. So secant squared theta is going to equal the square root of 17 over the square root of 16. And don't forget the plus or minus. So now I've got secant theta is going to equal plus or minus the square root of 17/4. Now, once again, now that we have this, we've kind of got a number here, we need to decide, is this going to be positive or negative? And so that's where I have to come back to the original problem. So we're in quadrant 4. Okay, so in quadrant 4, which functions are positive, which trig functions? All students take calculus, so only cosine is positive, and then also its reciprocal function, right? So that would be secant are positive. So those are the only two. Therefore, with this function, this is going to be positive, right? So this is positive. And then, now that I know this, I also know the value of cosine, right? Because I can use my reciprocal identity, secant of theta is equal to 1 over cosine of theta. So I can just flip the value of this. So cosine of theta is 4 over the square root of 17. I have to rationalize this, of course. This becomes cosine of theta equals 4 times the square root of 17/17. Whew, okay, so you can see that this can take a little bit of work to get through everything, but now I have, let's see, I have this value and I have this value. So let me clear some space and write those out, and then we'll find the last remaining trig values. All right, so now, how do we want to finish this? Well, we have some options. We can technically use like a quotient identity because now I know the value of tangent and I know the value of cosine, so I could work through it that way. I could also use one of the Pythagorean identities, right? So I've got sine squared theta plus cosine squared theta equals 1. There's a little bit of creative freedom when you're doing some of these. Personally, I like using the Pythagorean identities. I like having as few trig functions as possible, so I prefer not to use this one just because I don't want to have like all the division and multiplication and stuff like that. So I'm going to use the Pythagorean identity. So I'm going to use that cosine squared theta plus sine squared theta equals 1, and then I can plug this guy in. Oops, I'm sorry, I wrote this was 4. This should have been a 17, my bad. Okay, so now let's go ahead and kind of plug all of this in. So I actually want to remember the non-rationalized version of this, so maybe I'll write this in parentheses. Before I rationalize this, I think this was slightly easier to work with 4 over the square root of 17. So this is going to be the value that I plug in just to make my math a little bit easier. So I've got 4 over the square root of 17. You can totally work back and forth between the rationalized version and the non-rationalized version. That's okay. Okay, so got all this, so I'm going to get that sine squared theta is ultimately going to equal 1 minus 16 over 17. So I have sine squared theta equals 1 over 17. Therefore, sine of theta is going to equal plus or minus the square root of 1 over the square root of 17. Okay, so remember, we are in quadrant 4, and we talked about that in quadrant 4 only cosine and secant are going to be positive. Therefore, the sign for this will be negative. So I have sine of theta equals negative 1 over the square root of 17. However, I need to rationalize that now, so this becomes negative square root of 17 over 17. Okay, so I've got that, and then I can also figure out the value of cosecant of theta, which is found by just taking the reciprocal of this. So the that reciprocal would be negative square root of 17. And so now I have 1, 2, 3, 4, 5, 6 trig values, and I'm done. Okay, so that's another way that you can use some of the fundamental identities. And now I want to show you some other problems called transformations. So these are a very specific type of exercise that comes up with identities that are really there to force you to really have to use your noggin with writing out identities. So I wanted to show you just kind of a basic one. So write tangent x in terms of secant x. These can get harder, but I wanted to kind of just show you like a basic one. I have some more examples on this if you wanted to see how hard some of these can get. But let's start with the basic one here. So write tangent x in terms of secant x. Okay, so what you want to think of, ideally what would happen is that you have some convenient identity, say this one right here, where you have whatever you're trying to write, your one trig function in terms of the other. If you have an identity that kind of relates the two like this does, then this is kind of what you want to use. Okay, so write tangent x in terms of secant x. So what I'm going to do then is I'm going to write tangent squared x plus 1 equals secant squared x. So I'm just going to start with the identity. And then I want to have tangent equals. So this is what I want to have first. So I'm going to take tangent squared x equals secant squared x minus 1, and then I can just go ahead and take the square root. So this is going to be the square root of secant squared x minus 1. And what do you say? Am I missing anything here? Trick question. Yes, I am. I am missing the plus or minus sign right there. So make sure that you're not forgetting that. We don't have any context of what quadrant we're in, so we have to include the plus or minus sign in this case. Okay, and so for the last two examples, again, just kind of playing around with identities. So write the following only in terms of sine and cosine and simplify until no quotients appear and functions are in theta only. So I'm going to show you what can happen with these. Okay, so I've got cosecant of theta times cosine of theta times tangent of theta. So what this is really asking us to do is to rewrite all of this in terms of sine and cosine. No problem, right? So cosecant is sine of theta. I can't rewrite cosine of theta because it's already in terms of cosine. And then tangent I'm going to rewrite as sine of theta over cosine of theta. So this is what the problem is asking us to do. And then from here, it really wants us to simplify as much as we can. And you'll notice, right, the sines cancel out, cosines cancel out. So, oh my God, I'm just left with 1. So in this case, like after I write everything out, that's all I'm left with. And so that's totally fine. Okay, so let's compare that then to this other question. So cosine theta times cosine theta minus secant theta. Okay, so you have some options of how to handle this, I guess. So I could rewrite this as cosine theta times cosine theta minus 1 over cosine theta, and now I can distribute so that this becomes cosine squared theta minus 1. Okay, so we want to write this in the fewest amount of terms possible. That's the goal. So if you can think of, say, any other identities that might relate to this where we could write this in fewer terms, that's what we want to do. And so if I think back to my Pythagorean identity here, so I have this identity. How can I use this identity to rewrite this little expression that I've got here? Well, let me write that out one more time. So I had sine squared theta plus cosine squared theta equals 1. Okay, so what if I wanted to have cosine squared theta minus 1? How would that be possible? Well, I can get to cosine squared theta minus 1 if I subtract 1 and subtract sine squared theta. Okay, so you see how I did that? So then these sine squared thetas drop out, these 1's drop out. So I've got sine squared theta minus 1 equals negative sine squared theta. So my final answer then is negative sine squared theta. And so that's like the most simplified form. So you're really going to be kind of playing around with these identities. And you're going to find that there's not always one way to do it. I have a lot more examples on these types of problems because I knew that they require some more creative thinking and they don't always have like one direct path. So I've got lots of other videos where I kind of try to show you that and give you a little more confidence with that. Otherwise, thanks for watching, guys. I'll catch you in the next video.